Gravity question. All right, here's what we know so far. Newton came up with 3 laws of motion, and he left a couple of things unsaid initially. All right, so here's the apple. And when you let it go, I think this is your test number 4, I believe. According to test number 4, is gravity a force? I said. And you guys said, God knows what you guys said, despite the fact that this was discussed in detail more than on one occasion, guys. We discussed this like time and time again. And I'm not sure if you guys are not paying attention or you guys are paying attention, but you're somehow paying attention to the wrong stuff. All right, how do you know if gravity is a force? You know gravity is a force because what does a force do? It causes acceleration. That's it. All right, everything else is poetry. I'm not interested in poetry here. All right, you guys wrote a lot of stuff that lacks substance. All right, so it's got mass. Force acting on the mass is going to cause it to accelerate. It's going to fall at a constant rate, which is roughly about 10 meters per second squared, roughly. So gravity is a force. How do we know? Because falling objects accelerate. Next question, question number 2 from test number 4 or 5. Does gravity extend all the way out to the moon? And once again, I get these poetic responses as if you guys have done no physics at all. All right, as if it made no impact. Oh my God, look at the flat Earth. All right, so does gravity extend all the way out to the moon? There are 2 answers to that question. One answer goes like this. If it didn't, what would happen? All right, so here's the moon. If gravity didn't extend all the way out to the moon, what would happen to the moon? Straight line. Yeah, go ahead.
It would continue in a straight line forever.
Give yourself 5 points. I mean, it would move in a straight line forever. Okay, so what is that? Inertia, right? So instead, here's what the moon does. Orbits the Earth. It's still moving at constant speed, but it's not moving in a straight line. Speed hasn't changed, but the direction has. All right, given the fact that the direction is changing, and given the fact that this is centripetal motion, which means that it's going to have an acceleration inward towards the center. And acceleration can only be caused by a force, and the force is going to be in the same direction. So what that means is whatever the force that pulls the apple down is the same force extending all the way out to the moon. So answer to the question, hey, does gravity extend all the way out to the moon? Of course it does. If it didn't, the moon would have gone in a straight line at a constant speed. That answer is worth only 1 point. The real answer is, hey, yes, gravity extends all the way out to the moon because the moon accelerates towards the Earth. And then what causes the acceleration is this force of gravity. All right, so the apple falls because of gravity, and moon orbits the Earth because of gravity. All right, so if that's the case, if the apple falls because of gravity, why doesn't the moon also fall from the sky? So that's what Newton was asking. All right, this animation is not going to work. I don't know why. This newest version of PowerPoint is not like AVI files. All right, if the Earth pulls, if gravity extends all the way out to the moon, why doesn't the moon also fall from the sky? If gravity extends all the way out to the moon, if gravity extends all the way out to the moon, can you be weightless in space between here and the moon? All right, guys, you get your weight from gravity. If gravity extends all the way out to the moon, is there any place between here and the moon where you can feel weightless? Is there any place between here and the moon? Well, here's what you know. At least you know gravity extends all the way out here, right? So is there any place between here and the moon you would be weightless? That question is... All right, so that's not the right answer, obviously. All right, so is there any place between here and the moon you feel weightless between these 2 points? Yes or no?
Yeah.
Okay, where?
In a falling elevator.
I'm just gonna... There's no falling out. Is there any place between here and the moon would you become weightless?
Yeah, isn't it like once you exit the atmosphere, pretty much the astronauts start to feel weightless, or is it a little further?
No, I'm talking about being weightless.
When you reach terminal velocity in a skydive.
Is there any place between here and there you will become weightless in space? All right, everything. I think when you skydive, you give yourself 5 points, but that's not what we were discussing, right? We're talking about being absolutely weightless between these 2 points. Is there any place between these 2 points in space? Given the fact that gravity extends all the way out to the moon, and gravity is the amount of force acting on it, right? The amount of gravitational force acting on it becomes your weight. So your weight is the amount of gravitational force acting on it. So given the fact that the gravity extends all the way out to the moon, is there any place between these 2 points in space you would be weightless, where you have no gravity acting on you? That's what I'm asking. Where do you get the gravity from? Gravitational force. It comes from the Earth, right? How do we know that? Because falling objects accelerate towards the center of the Earth. All right, and in circular motion, the acceleration is also directed towards the center of the circle. At the center of the circle, you have the center of the Earth. So which means that the force that pulls the apple down extends all the way out to the moon. So if that's the case, is there any place between the moon and the Earth where you would become weightless? Answer to that question is no. I mean, in theory, there's also the force of gravity from the moon. So at some point between, if you have this radial axis, at some point between the moon and the Earth, very close to the moon, there's probably a place where you will feel weightless. You will become weightless because the net gravitational force acting on you is going to be 0. But in reality, aside from that particular point, any other point within this line, you cannot become weightless. It's out of the question. So astronauts cannot be weightless in space. That's what it means. If Newton is correct, you cannot be weightless in space. If Newton is correct, just about the only place in the universe you will become weightless is in deep, 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 deep space, almost weightless, which means that you literally have to be millions upon millions upon millions of light years away from the nearest planet or a star. All right, so there's no place between here all the way up to the moon, with the exception of one single point, where you will become weightless. So if that's the case, astronauts, why do they feel weightless? Why do they appear weightless? All right, so in order to answer these questions, Newton came up with the law of gravity.
Lights, please. Just dim the lights. The law of gravitation was first formulated by the English physicist Sir Isaac Newton in 1684. And then he did some other things. But that was a long time ago. Today we live here on the planet Earth, where gravity creates our weight. If we lived on Jupiter, we would all weigh more, because it has more mass than Earth, and so the gravity is greater. If we lived on the moon, which has less mass, we would all weigh less, because the gravity is less. The end. For a written transcript of this show, listen to it again and write down everything you hear.
When did Newton live, roughly? Based on this little clip that you saw. Did he live like in 1960s? Do you think he was a hippie? In 1950s? Did he live like 2,000 years ago? Do you think he knew Jesus? Do you guys think he had a pet dinosaur? When do you think this guy lived? Give and take. Give and take. How many years ago?
400?
1600s. Isla says. All right, 1600s, guys. Isla, give yourself 5 points. 1600s, guys. Mid to late 1600s. Roughly about 350 years ago. All right, so this guy lived roughly about 350 years ago. And then here's what he came up with. He knew that the force of gravity was something generated by the mass itself. So what generates mass? What generates force is the mass itself. So he came up with the laws of motion. On top of that, he came up with the law of gravity. So as far as Newton is concerned, what generates gravity is the mass itself. All right, so you got the small mass, and then you got the big mass. And these masses will be attracted to each other through the force of gravity. So you got the small mass, and you also have the big mass. All right, so F is going to represent the force of gravity. He says the gravitational force is going to be directly proportional to the product of the masses. Product means multiplication. When you say product, it means multiplication of the masses. So it's going to be directly proportional to the product of the masses. All right, so the bigger the masses are, the bigger the force is going to be. All right, so it's going to be directly proportional to the product of the masses. And then it's going to diminish with distance, radial distance between the masses. All right, so this R is going to represent the radial distance. So the force is going to diminish inversely with the distance, radial distance. And then later he noticed that this force is going to diminish with the square of the radial distance. Boom. This is known as an inverse square law. All right, so if you put these two facts together, all of a sudden you come up with a formula that looks like this. And the force is going to be directly proportional to the product of the masses. And it's going to be inversely proportional to the square of the distance. Okay. And then when you try to apply this to a real life case, here's what happens. It gets really, really weird. All right, so let's use a person who's interested in someone. All right, so let's pretend that he's interested in her and she's not interested. There's no physical attraction. There's no chemistry. So is it possible for him to be able to attract her gravitationally if that's the case? All right. So let's take a look at this scenario. All right, so for him to be able to attract her gravitationally, he needs to become really massive. All right, the easiest way to become massive is to eat. let's pretend that potentially by eating, you could get up to 300 pounds. She's gonna remain small. Assume that she's like a 100-pound petite. I also imagine that the closest that he could get to her is gonna be about 1 meter. It's about 3.28 feet without any physical. So how much gravitational pull is he gonna have on her if that's the case? What is the amount of gravitational attraction? If you apply the Newton's law just directly as is, I mean, you know that the force of gravity depends on the product of the masses. This woman is going to remain petite, and he's going to get big. And then closer he gets to her, the bigger the force is going to become, right? Force of attraction. So you run the numbers, only to realize that at a distance of 3.28 feet, almost a yard, the amount of force that they will be feeling towards each other is going to be about 1,400 pounds, guys, if you apply that formula directly. What that means is the big guy's attraction to her is going to be about 4.5 times his body weight, and her attraction to him is going to be about 14 times her body weight. And notice that now she's more attracted to him than he is to her, right? This is otherwise known as the big daddy syndrome, if there is such a thing. Except that life doesn't work that way. That analogy worked. Smaller objects would be attracted to us, and then we would be attracted to bigger.
Geico Auto Insurance, we handle your claim quickly, so you don't have to bum a ride to work.
So what's missing here? I mean, if you're applying the logic directly, you end up getting these absurd numbers. And so what's missing here is the strength of gravity is missing, right? Because the amount of gravitational pull that we feel towards each other is very small. He can get big. He's going to become more massive. He's going to get fatter or whatever. It's not going to increase his gravitational pull on her. It's not going to happen. The reason why it's not going to happen is because there's something extra going on. The extra stuff which is going on is everything needs to get multiplied by this capital G. Capital G is otherwise known as the universal gravitational constant. It gives you the strength of gravity. This is a very small number. So what happens is this formula gets adjusted for reality. Everything is going to get multiplied by this capital G. Capital G is known as the universal gravitational constant. All right. So that's the strength of gravity. All right. So F is the force of gravity or gravitational force. M and capital M. These are the mass or masses. R is the distance between the masses. And I want you to notice that this distance is measured with respect to the center of mass. The center of mass is the center of balance. So R is that distance. And then we have capital G. Capital G is the universal gravitational constant. You got your universal gravitational constant. Force of gravity, expressed in terms of newtons. Masses, kilograms. Distance, meters. And capital G is a measured number. All right, it's 6.69, I think. 6.67 times 10 minus 11. 6.67 times 10 minus 11. It's going to be Newton meter squared per kilogram squared. I don't like it. It's a very small number because you got 10 zeros before you hit the first number. It's a very small number, which means that gravity is extremely weak. Because this is a very small number, gravity is going to be extremely weak. So that's the strength of gravity. All right, so with this universal gravitational constant included in the equation, all of a sudden the gravitational force between any two people is going to be unnoticeably small. This is microscopic. So that's what happens. All right, so this is the mathematical expression for the force of gravity. It's generated by the mass or masses. So it's going to be directly proportional to the product of the masses. It's going to be inversely proportional to the square of the distance, and then the strength of gravity, universal gravitational constant, multiplies everything.